Organizing data in a train yard means managing elements that aren't stored in a single continuous line. Instead, the cargo cars you need are scattered across different tracks, parked wherever the yard had an open spot. This diagram shows two different ways to store data. On the left is a traditional array. It acts like a rigid, numbered parking garage, where every item has a fixed, predictable slot. On the right, a linked list lets data scattered, connected by coupling chains. Each car, or node, has two parts, the cargo storing data and the pointer chain grabbing the next car in sequence. Because these cars aren't parked in a row, you can't jump directly to the middle. To read the sequence, you must find the first car, the head, and follow the chains one by one. You reach the end at the null terminator, a car with a chain connecting to nothing. By letting the chains dictate the logical order, we can reorganize the entire sequence simply by unhooking and rehooking the connections. We never have to pick up and relocate the heavy cargo cars themselves. This diagram shows a classic computer science problem, merging two sorted linked lists. We have train A, carrying cars weighing 1, 3, and 5 tons. Parallel to it is train B, carrying cars weighing 2 and 4 tons. Both are already sorted from lightest to heaviest, and our job is to merge them into a single sorted train. Remember our rule. These cargo cars are too heavy to lift and move to a new track. We can only manipulate the coupling chains between them. The immediate problem is figuring out how to start. If we are building a brand new logical sequence from scratch, our first coupling chain has no predecessor to hook onto. We solve this by creating a dummy node. This is a temporary, empty locomotive engine that holds no actual data. We drop it onto the tracks for one reason: to provide a guaranteed null-null node that our very first coupling chain can anchor to. In code, the dummy node acts as a reliable predecessor. It prevents the algorithm from failing when it tries to attach data to an empty head pointer. Looking at this diagram, we begin the sorting loop standing at the dummy engine. We look at the front of both tracks and compare the options. Train A offers a 1-ton car, and Train B offers a 2-ton car. Since 1 is lighter than 2, the dummy engine snaps its chain onto Train A's 1-ton car. We then step forward along that chain, moving our current position to the 1-ton car, so we can evaluate the next link. From here, we compare the next available cars. We look at Train A's 3-ton car and compare against Train B's 2-ton car. Because 2 is lighter than 3, we take the coupling chain from our 1-ton car, stretch it across the tracks, and hook it onto Train B's 2-ton car. And again, we step forward to our new position on the 2-ton car. This is the entire repeating loop. We simply weave back and forth between the two tracks, comparing the front cars and snapping the chain onto the lighter option to build a single sequence. By splicing the lists together this way, we've organized the sequence entirely through pointer manipulation. We didn't waste resources creating new nodes or shifting heavy data around. We just reorganized the chains. Let's look at this diagram to understand the base case. What happens when the tracks are uneven? Here, Train B's track runs out, but Train A still has a 10-ton and a 12-ton car sitting on the rails. Since the remaining cars on Train A are already sorted and chained to each other, we don't need to check them individually. We simply hook our active chain directly to the 10-ton car, instantly incorporating the rest into the sequence. The sorting is finished, but we have one minor cleanup task left. Our sorted sequence is still anchored to that temporary dummy engine we placed at the beginning. As you can see in the diagram, we solve this by returning dummy.next. This tells the system to ignore the fake locomotive, step over the very first chain, and start reading the actual merged list at the 1-ton cargo car. When you tackle linked list problems, remember the train yard. Focus on manipulating the coupling chains rather than moving the data, and use the dummy node to handle those tricky starting pointers.